Okay. Okay, let's begin again. So yesterday we talked about slow relaxation in systems with disorder and frustration. The basic phenomenology is described by this phenomenon called aging. Aging basically means that if we produce a quench from a high temperature initial state to a low temperature, the system loses quickly kinetic energy, tries to relax to equilibrium, but because of frustration, it struggles to relax. So the basic protocol is a quench at t equals 0. After this sudden quench, we fix time called T waiting. And from T waiting, we begin to measure some observable. So particularly interesting observables are two-time quantities, like correlations and responses. So for example, we begin to measure at T waiting, and then we record at time T. After T waiting, we can compute the 2 times correlation. Autocorrelation, in particular. As a function of tau. Yes. This is the waiting. This is the time we wait from the quench until we begin to measure. Yeah, okay. T is the waiting plus tau. And T prime is the waiting. So we are considering T prime less than T. Okay? Tau is the difference, is T minus T prime. So a useful way to look at this phenomenology is, for example, to plot autocorrelation function defined in that way for a spin system, for example, as a function of the difference between the longest time, the time at which we measure, and the waiting time, the time at which we begin to measure. So we let the system relax for some time, that is the waiting time. And the question is that in disordered systems, the waiting time matters. So the system typically stays for long times out of equilibrium. So 2-time quantities does not quickly relax to stationary dynamics. In stationary dynamics, in equilibrium dynamics, these quantities should depend only on tau, on the difference between the 2 times. But so we are arguing that in a system with strong disorder, with quenching disorder, this does not happen quickly. So in general, in the laboratory, the waiting time, the time from, well, this protocol that is a quench, that is a sudden quench, I'm thinking of quenching in temperature, thermal quench, hence, say the observation, the observable will depend on the waiting time, and of course, on the longest time at which we measure. So, if we wait a particular waiting time, we will observe that the system relaxes a bit and develops a plateau, still for a large value of the correlation, so the system does not decorrelate much until some time scale, after which it decorrelates. these curves depend on the waiting time. So for different waiting times, the plateau extends for longer and longer time scales. So again, there are 3 waiting times. 1, so 3 experiments. Three different quenches. The first quench, we wait some waiting time, then we repeat the experiment, and we wait a different waiting time, for example, a larger waiting time. We will observe that this plateau, that is called the quasi-equilibrium regime, gets longer and longer as the waiting time grows. So initially, the picture is that the system enters a kind of local equilibrium sector. So for example, we quench from here, from some point, this is the energy landscape, the potential energy landscape. So we quench, and the system relaxes initially in a limited sector of phase space, because the energy landscape is rough. We say that it is rough. It has many, many local minima, separated by energy barriers, in general, with a multitude of scales. So this is the first sector in which we waited a waiting time, begin to measure, the system relaxes quickly, exponentially, to some region, and it stays there for some time. Because this is a fast relaxation, for different waiting times, the system will relax to the nearby local equilibrium. And so it will develop a time translation invariant regime initially. This is the quasi-equilibrium regime. Yes, yes, please.
Yeah, I mean, we're discussing classical systems, right?
Yeah,
so
yeah.
It's like, I don't really understand why we discuss everything in terms of like weighting, because it's classical, right? So I could just like measure everything all the time and have knowledge about this correlation function. So why is this waiting time the right way to plot these things?
No, if you are in a laboratory, for example, and you prepare your sample in a fluid state at high temperature, and then you quench, say you put it in a freezer at a much lower temperature, the system will try to relax to equilibrium. So initially, you produce the quench. This is an instantaneous quench.
But the quench
this is T equals 0.
But the quench is always the same, right? It has nothing to do with T waiting what the quench is, right? The quench is instantaneous and always the same.
The quench is instantaneous.
Okay.
But you wait a T waiting until you begin to measure. That's the point.
But why?
Until you begin to observe the system.
Okay.
And if you
Okay?
never observe the system, so the system never gets out of this quasi-equilibrium state.
No, but it's classical. It does whatever it wants, I guess.
The longer the T waiting, the longer the quasi-equilibrium state lasts.
T waiting is infinite, so the system will
Yeah, the system will stay
in the plateau forever.
will stay in the plateau. Yeah, will stay in the plateau.
But it's a classical system, right? I mean, me observing or not shouldn't matter.
But it's the quench that making the relaxation, right? It's because I do the quench that the system relaxes, right?
The system is trying to relax to equilibrium. You have some temperature, and you quench it, say, to T equals 0, from a high temperature initial condition to a low temperature initial final condition. The system tries to equilibrate, tries to thermalize.
But I mean, I do the same quench for any value of T waiting, right? It's an instantaneous quench.
Yes, you produce the same quench in the sense that you put it in contact with a heat reservoir at the same temperature.
Okay, but since it's classical and measuring doesn't impact the system, I mean, how can the equilibration time depend on when I start to measure?
No, the problem is that in general, these systems do not equilibrate. That's why they depend on the waiting time. The observation depends on the waiting time.
But eventually, okay, I don't get it, but okay, I'll just keep saying.
The quasi-equilibrium regime is not the true equilibrium. So the system gets stuck maybe for infinite time scales in,
Well, maybe,
in,
or
local equilibrium. Because, for example, the system relaxes to some limited sector of a space, and it finds large energy barriers that, for example, probably during laboratory time scales, it cannot go out from them. So you think that the system is in equilibrium, but in fact, it is not really in equilibrium at the hypothetical temperature that it should be, the temperature of the quench.
But does measuring something? No, right? It's classical.
No, I don't understand what do you mean by
I mean,
classical.
it's classical, so measuring doesn't do, the system does whatever it wants, no matter if I observe it or not, right? So I don't understand why.
Well, maybe we can discuss this later. I don't understand the question.
I think he's asking why essentially the point at which the curve goes down depends on when you start to observe the system. It looks like by measuring, you're altering the dynamics of the system. I think from his perspective, is that what you're asking?
Yeah, but it's classical, right?
It's classical, yes.
Please repeat the argument.
He's asking why the length of the plateau depends on the
waiting time.
Yes, the length of the plateau, why it depends on the waiting time. Because it looks like by changing the timing at which you make the measurement, you change the dynamics of the system.
Say the length of the plateau depends on the waiting time, because the longer the waiting time, the more deeper in the energy landscape the system gets. So it will stay. This is the energy landscape, the classical energy landscape, if you can think of the potential energy landscape. So it will stay in a limited sector for some time, and then it could get through the energy barriers and relax a bit more and go to deeper minima in the energy landscape. So there are a hierarchy of time scales in this process. Because, for example, in a spin glass, even the free energy has many minima.
And why are deeper, I mean, how hard it is to get out of this lower minimum doesn't really depend on the absolute energy, right? So why is there this hierarchy?
It will depend on the barriers, no? You will have some, say,
why does it take longer to get out of that lower minima compared to the upper one?
no, because the barriers in a disordered system, you have a hierarchy of height of the barriers. So the system will be near barriers of many different heights. Okay? So initially, it will stay for some time in a region that is nearby and at say, typical of higher temperatures, surrounded by not so high barriers. After some time, by thermal fluctuations in this case, it will be able to go out of this region.
So let's say I wait enough time so that we're in the second minima.
Then you go to the second minima.
But then looking at this graph, because the memory regime is longer for longer wait times,
Yeah.
that would mean that on average, the lower minima are harder to get out of, right?
Yeah, are harder to get out.
And
Yeah,
why?
yeah. Because, say, the typical equilibrium temperature will be some energy scale that we can think that is lower than these scales. So as the system gets in this region, it will have more, say, more entropy. It will have to flow through a larger phase space in order to relax. As the system goes down and down, it gets more trapped and trapped in the region it reached. Okay? Another important detail that I have not speak about is that this is a picture in one dimension, but what is happening is in n dimensions with n large. So this is an hypersurface in n dimensions with n large. So typically, the system will, during the relaxation, find many local minima and saddles, typically saddles of any index, say, with some number of directions unstable and some number stable. So the energy landscape is really complex. In a disordered system, typically you have an exponential number of critical points of the energy landscape. We will compute them now for the SSK model that is much simpler. But in general, there is an exponential number. So the system at some point is near some critical point with n directions, and it has to go out of them to relax because the equilibrium temperature or the typical energy at that temperature is lower at some time. It can reach that, but in general, it will not reach if the temperature of the quench is low enough. Okay. We can talk more after the lecture. Okay. Yeah. Now, in models, of course, in a particular realization of the disorder, you will have one landscape defined by that realization. But, say, statistically, you are interested in average, in the average behavior. And in models of glassy systems, spin glasses, and systems, magnetic systems in random fields, for example, it turns out that there is a hierarchy of energy minima, say, of critical points. But these are models. These are models. Excuse me, I didn't understand the question.
How to understand that average? What are you averaging over?
Over realizations of the disorder.
So for one realization, it's not random, then for different waiting times, it's always shifting to longer plateaus.
For any realization, for a single realization, the same happens. The same happens. Say, the longer the waiting time, the more trapped the system gets, and the longer it will take to go out to equilibrium. But you will have fluctuations, of course, from sample to sample. Okay, so let's go on. This is what happens. I mean, in a glass, for example, when you prepare a glass in a liquid state and you cool it to the solid state through the glass transition, it will try to equilibrate, as we said yesterday. It will try to equilibrate at room temperature. But in fact, the system does not equilibrate. It struggles to equilibrate because of frustration. The frustration produces this phenomenology that is, I mean, it is saying that the system, in fact, is out of equilibrium. We are observing a dynamics that is not stationary. So the system is out of equilibrium. If we look at quantities that depend on 2 times, for example, they will depend on both times. And a large class of systems that are called glassy generically show this picture of relaxation with, this is an interpretation, of course, this quasi-equilibrium regime that we are interpreting as a fast initial relaxation and the system staying for some time in a limited sector of phase space and then relaxing is an interpretation. But this is the interpretation that emerges when you study models. And well, and here you can identify these two clearly different regimes, a regime that is stationary, but it is limited in time, so it is quasi-equilibrium. Because if we wait enough, it will relax. The system will go out from the region it is, and it will relax. And this, of course, the state vector of the system lives in a very high-dimensional space. So this is n-dimensional space. So the critical points of the energy landscape are critical points in n dimensions. So in general, there will be a number of directions stable and a number of directions unstable. Typically, the critical points will be saddle points. And it turns out that as the system gets to lower, to deeper and deeper minima, it will find more stable critical points. So it will approach, say, the ground state, which is stable, a minimum, or local minima, But in general, they will be saddles. Let's compute how this works in the SSK model.
There's some information which value you find the plateau, or is that independent of the model?
Which value of the correlation?
Yeah,
The plateau will go to a value that's called the Edwards-Anderson order parameter. That is basically the size of the correlated region that it finds when the waiting time is long enough. Because, of course, if the waiting time is very small, the relaxation is quick, as we saw yesterday in another picture. But this phenomenology is valid for long waiting times. So if waiting time is long, this is a typical region in which has some size, and this value is the measure of the size of this region in which the system is correlated. Well, in the literature, it's called the Edwards-Anderson order parameter, spin glasses. In the models you can compute, it will depend on the temperature. For the calculations we did yesterday at 0 temperature, it is 1, because the system is going to the ground state. But if the quench is to a finite temperature, this level will depend on temperature. So the order parameter will depend on temperature, of course. Okay. No, a saddle typically is a critical point of the energy surface in n dimensions. Each dimension is represented, for example, by the eigenvectors of the J matrix. A certain number of positive eigenvalues of the Hessian. Say, the second derivative measures the stability of the critical points. You will have critical points with n dimensions and coordinates, and the second derivative, you diagonalize, compute the eigenvalues, and the number of positive eigenvalues will mean that directions are stable, and number of negative eigenvalues means that directions are unstable. We will compute them for the SSK model. So the SSK model is a good example for understanding this a little bit. Before computing the critical points in the SSK model, let's compute a relation between the Lagrange multiplier that we saw yesterday that enforces the spherical constraint. Remember the energy or the Hamiltonian of the SSK model. So we can introduce a Lagrange multiplier that enforces the spherical constraint. So the state vector of the system means are real. Remember that we relax the condition of the Ising Hamiltonian. These spins are real, but the state vector lives in a sphere in n dimensions, in an n minus one dimensional sphere. The Lagrange multiplier has to enforce the spherical constraint for each time. And we computed this yesterday for the SSK model. That is this model where the coupling constants are chosen as a real Gaussians, so from the Gaussian orthogonal ensemble. The Langevin dynamics, we define the Langevin dynamics, I would say the typical dynamics for a classical system that guarantees that the relaxation will flow to equilibrium, that the system will sample the Boltzmann measure at long times. For fixed time, this is basically the gradient of the potential, say conservative force. Well, we have already incorporated the constraint in the Hamiltonian, so plus the noise, plus the random noise. Now you see, at zero temperature, that was the example that we focused yesterday, at zero temperature, the relaxation, this is for I1 to n. Of course, we have n equations coupled through the energy, the Hamiltonian. At zero temperature, this averages to 0, and the relaxation is a gradient descent. So this is the gradient in the energy landscape. So say necessarily if the system relaxes from an initial state and finds a local minimum in that relaxation, it will stay there at zero temperature, okay? It will relax through the gradient. This is a gradient descent, and it will stay there. But we saw yesterday that that does not happen in the model, in the SSK model. It relaxes, in fact. It shows that different regimes. So something is telling a priori that the critical points that it finds in the way to the relaxation are not local minima. Maybe they are saddles. So we will see that, in fact, they are saddles. So saddles have some number of stable directions and some other number of unstable directions. So if the system finds saddles, it may stay near each saddle for a while. Say, the more stable the saddle, the longer the time the system will be around this saddle, but at some time it will find the direction to flow out. So think that this happens in a very high dimensional space. So if the number of unstable directions is small, the system will stay for a long time there until it finds the direction that allows it to go out. This is the picture we have for this relaxation. At finite temperature, of course, it will have thermal fluctuations, and the system will be able to relax through through barrier crossing, through activation. So at the finite temperature, there will be a competition between barrier crossing, say activation, and relaxation, more kind of entropic relaxation through flow through saddles, because most of the critical points are saddles, so they are not completely stable. Okay, so it is complex. That is why this dynamics is complex, because the system is flowing and finding a region dominated by these saddles that in general are exponential in n, the number of saddles, so there are many. In fact, the number goes to infinity exponentially, and the relaxation is slow. So let's compute this at t equals 0 for the SSK model. So the gradient of the energy minus the gradient will be the local field. Plus the Lagrange multiplier times psi of t. Let's multiply on both sides by 1 over m Si at t prime. So we'll have on the left 1 over n and sum over I. So we'll have sum over I, derivative of SIT prime with respect to t. And on the right, we will have sum on y and j, jyj, SIT, or SJT, SIT prime, plus z of t, sum over I, Si of t prime square. No, sum of t, excuse me, Si of t prime. Now let's no, it's the derivative with respect to t only. Of one time, only of t, only with respect to t. Only on the first, only on the first. Let's put this here. SIT prime. Now let's t prime go to t. If we let t be equal to t prime and we sum over n, we apply the spherical constraint, and this derivative will be 0.
On the right side, it needs 1 over n also?
Yes. Thank you. Yeah. All has 1 over n and 1 over n. Here, no. Minus 1/2. 1/2 here. With a relative to y. No. The 2 goes out. Say, the minus is cancelled with this minus. And as this is a sum on y and j from 1 to n, there are 2 terms when you derive relative to one particular index. So the 1/2 also goes out. So this remains. And in this side, we write it this way in order that it cancels with the 2 when you derive. Yeah, here's minus. Thank you. Okay, thank you. One over n, let me confirm. Okay, 1 over n. So when we let t prime go to t, this will be s of t squared. So summing over I and dividing by n, say, and fixing the spherical constraint, this derivative will give 0. So from there, we can extract a relation between the Lagrange multiplier. Here, again, this will give 1 when t is equal to t prime because of the spherical constraint. And this is the energy density, say the energy per site. So the Lagrange multiplier is equal to the energy per site. So Z of t will be equal to h, to minus h, okay, over n. With a 2. Let's define the energy density as minus 1/2 sum in y and j, jij, si, sj, over n. So z of t will be minus, okay, 2e. So this is the energy landscape. I went through this computation in order to get this relation between the Lagrange multiplier and this energy density, because we will see in the following that at the critical points, the Lagrange multiplier is also equal to the eigenvalues of the J matrix. So the eigenvalues of the J matrix work as a label for the critical points. They are equal to the energies at the critical points. So we can order the critical points through the eigenvalues of the J matrix. We will see that in a minute in the following. let's come back to the dynamical equations. But now, let's write them in the eigenvector basis. In which the equations are decoupled. So it is simpler to obtain the results. So minus 1/2 sum y lambda y. These are the projections in the directions of the eigenvectors. Plus z of t, y of t square. Okay. Yeah. So the Langevin equation at 0 temperature reads the derivative of y of t with respect to the time t. It will be lambda I minus z times y I of t. Okay? For I equal 1 to n. The stationary points of the dynamics are when the left-hand side equals 0, so we have to solve this set of equations. So see, there is a trivial solution that is all of the y coordinates equal to 0, but it does not satisfy the spherical constraint. So it is trivial, and it is not a good solution for us because the y's must satisfy also the spherical constraint. So necessarily z must be equal to some of the eigenvalues. These are the n eigenvalues of the disordered matrix. So let's say that z equals lambda s for some index s. Then the value of the coordinate is arbitrary, and all the others, say the ys arbitrary a priori, and all the other coordinates different from the s coordinate must be 0 because the Lagrange multiplier equals one of the eigenvalues. We are supposing that the system is non-degenerate, so the eigenvalues are different. So if it's equal to lambda s, it is different from the others. So the other coordinate should be 0. So at the critical point, the projections on the eigenvectors of the Jij matrix say the y variables are such that ys equals plus minus square root of n. This is in order to satisfy the spherical constraint. And yk equals to 0 for all k different from S. Okay, so typically we have a configuration that will have zeros, plus minus square root of n, and zeros. These are the states at the stationary points of the dynamics, at the critical points. So they are the coordinate directions of a configuration space. So from here, we can count how many stationary points there are for the SSK model. There are 2n. For each eigenvalue, we have 2 critical points. So there are n eigenvalues, we have 2n critical points. And furthermore, they can be labeled by the eigenvalues, because at each critical point corresponds to the Lagrange multiplier being equal to one of the eigenvalues. And as we saw before, the Lagrange multiplier is also proportional to the energy density. So the energy at each critical point can be labeled by the eigenvalues of the J matrix. So we can order them. If we order the eigenvalues, for example, in increasing order, for the Gaussian orthogonal ensemble, remember that this will be near 2, the Wigner distribution, and this will be near -2. The density of eigenvalues is a semicircle law between 2 and -2. So we can order the eigenvalues in increasing order, such as lambda n corresponds to the maximum eigenvalue and lambda 1 to the minimum. Yeah, we are considering that the system is not degenerate. Okay? No, that doesn't has to do with frustration. So the degeneracy in a disordered system is not related to frustration, the degeneracy of the eigenvalues. In general, say in the Gaussian orthogonal ensemble, so disordered matrices with Gaussian entries, you will not have degeneracy. Of course, this is when this goes to the continuum for n going to infinity. But for finite n, you have n eigenvalues that in general will not be degenerate. So you see, we can label the stationary points, the energy of the stationary points, with the eigenvalues, the energy density, for example. Because we know that at each eigenvalue, there is a relation between the energy and the corresponding eigenvalue. So Z must be equal to lambda S, so the energy will be minus lambda S over 2. say, for S between 1 and n, we can label the energy of each critical point. Yeah, now let's see that. So these are the critical points. We concluded that they are 2n in number. And the energies at each critical point are proportional to the eigenvalues of the J matrix. Now let's see the stability of these critical points, that this will tell something about the relaxation. So for that, we have to compute the Hessian, that is the matrix of second derivatives. Okay. From what I said before, that in general, in a disordered system, the number of critical points scales exponentially with n, you see that here it's different. They are much less in number. They scale with n. There are exactly 2n critical points. But this is a really very simple model of a spin glass in this case. More complex models of spin glasses have a much larger number of critical points. So this, as I said yesterday, this is a simple model from all points of view. This is another way of seeing at the structure of the energy landscape. But nevertheless, it shows qualitatively, say, the phenomenology of slow relaxation and out of equilibrium relaxation. So it is not trivial. Well, stability of the critical points. Let's compute it. We have to compute the Hessian matrix. Well, sorry, I will use H. That is the Hessian. This is a matrix, and it will be given by the second derivative of the Hamiltonian. Now, let's change let's call it T. With respect to Si, with respect to Sj at a critical point. At the critical points. So when we derive again, say this is the first derivative, okay, that we did at 0 in order to compute the stationary points. So if we derive more with respect to, for example, to yj, we will have the eigenvalue okay. Let's write it in the original basis initially. In the original basis, this will give basically jij when we derive twice with respect to Si and Sj, minus Z times delta Yj. Okay, because the said term will have a derivative with respect to y, then we derive with respect to j, so only the diagonal term will be non-zero. So what are the eigenvalues of the Hessian matrix? Are the eigenvalues of J minus a diagonal term that is proportional to Z. So at the critical points, at the S critical point, the eigenvalues of Tyj, this is the Hessian, the eigenvalues are lambda k equal to the eigenvalues of Jij minus lambda s at the S critical point, okay? Minus lambda s. For k equal 1 to n. N eigenvalues of the Hessian matrix. So you can immediately see that there will be some eigenvalues that are positive, that directions will be stable, and some eigenvalues that will be negative, and that directions will be unstable. So again, depending on the critical point, we will have more or less negative and positive directions, and we can classify exactly the stability of each of the 2n critical points. So we will have two maxima in which all k's will be larger than s. There will be one zero eigenvalue that is a radial direction, that it is not important for this spherical model. Remember that the system, this model lives on an hypersphere, so the important directions for the dynamics are tangent to the sphere. So we look at the other eigenvalues. We will have two maxima, really, when all the k's are smaller than s. We will have two saddles of order n minus 1 with n minus 1 negative directions, two saddles of order n minus 2 with n minus 2 negative directions, and so on and so forth, until two minima, two saddles with all eigenvalues positive, that are two symmetric minima, because this system has this reflection symmetry. No, if you shift the mean of J, the situation changes. It will have another term corresponding to this shift. I am considering disorder variables that are Gaussian with zero mean. So I'm not considering ferromagnetic contribution to the Hamiltonian. So it is symmetric. It is symmetric with respect to zero. Yeah, if you include a ferromagnetic term, you will shift the eigenvalues, and it will change the stability of them. So these are saddles. So you see that we can classify them, as I said. There will be two maxima of index n minus 1. The index at the critical point of the surface is the number of negative eigenvalues of the Hessian at that critical point. So there will be two maxima, two saddle points of index n minus 2, two saddle points of index n minus 3, until two minima. At the minima, the energy equals minus lambda m over 2. remember that the energy density at each critical point equals minus lambda S over 2. So the ground state corresponds to the largest eigenvalue. Okay, the energy of the ground state is minus lambda n over 2, and it is a minimum. So this is the picture of the energy landscape of the SSK model. So the energy surface has 2n critical points. They are typically saddles. There are not many local minima. There are only 2 local minima that corresponds to the ground state. So that is why even at t equals 0, the model relaxes when we quench it to 0 temperature, as we did. Say, it does not find a local minimum in the relaxation. It will flow through saddles. And if the initial condition is a high temperature one, a disordered one, it initially will find saddles of high order, of high index. So with many unstable directions. So the system can flow outside of the region, say, dominated by these saddles. But as it flows deeper and deeper towards the ground state, because we are quenching to 0 temperature, it will be, say, flowing near regions in which the stationary points, the critical points of the landscape, has less and less unstable directions, are more and more stable as the system approaches the ground state. So the dynamics will become slower and slower because it struggles more and more to find these unstable directions to flow out. So imagine this is an n dimensions. No? The state of the system lives in n dimensions. So it will have some dimensions along which it can escape. It can go out and relax. And other directions that are stable at which the system will not be able to escape. If we put some temperature, if we quench to some finite temperature, there will be another phenomenology that, in spite of the saddle being near a local minimum, say with a few unstable directions, the system can activate, can fluctuate, and get out of a region by activation. But if we quench to 0 temperature, this is not the case. We are extracting all the kinetic energy, say, instantaneously. So this allows to see or to interpret or to understand the phenomenon of this slow out of equilibrium relaxation from the perspective of the landscape of the system, okay? Yeah. The lower the energy, the more stable will be the critical point. Yeah. This is for this model. Yeah. In general, it is very difficult to compute this for a general model. Say, because in general, for a model, say, with Ising spins, or for more complex models with quench disorder, you will have many more critical points, exponential in number, so it is even very difficult to compute the number of critical points. So there are special techniques to compute the number of critical points in general. For this model, this calculation, that is very simple. But, well, as I said, this illustrates the phenomenology. Yeah, you see, here the barriers are not important. The system flows through unstable directions that characterize the saddles. In fact, quenching to 0 temperature, if there would be local minima, So, in fact, we discovered that the landscape is like this, say in a picture, in a one-dimensional picture. So it has saddles with some stable direction and with some unstable directions. So it always has some directions from which it can escape. So it is not necessary for it to activate through a barrier. So in this sense, it is very, very simple, the landscape of this model. So there are no local minima, only the absolute minimum, that is the ground state. Okay? So this dynamics is governed by the flow through unstable directions in the saddles, at the saddles. In general, C depends on time. Yeah, but for this, we are computing C at the critical points. At the critical points. But yes, say, as time goes by, you can think of a time-dependent Hessian. Yeah, C depends on time. But that means that if you compute the matrix of second derivatives at an arbitrary time, the system will be at some point in the surface. Say, it will be here. So it will have a number of unstable directions that will be governed by the value of Z at that time. So you can think like that the Hessian is time dependent. Say, in this analysis, we focus on the critical points because, say, again, if there would be local minima, the system would flow to the nearby critical point at 0 temperature and stay there. It does not stay there because they are saddles. They have some unstable directions. Well, so this plot of the semicircle law shifted goes in the direction of your point. So as the system explores deeper and deeper energy levels, the eigenvalues of the Hessian will be more and more stable. Say, the Hessian will have more and more positive eigenvalues. So the distribution of eigenvalues is still a semicircle, but it is shifting in time. You see that initially, from a high temperature initial condition, there will be basically half of the eigenvalues will be positive and half will be negative. As time goes by this process that we can interpret as governed by the time dependence of Z, more and more eigenvalues will be positive. So we can think that the Wigner semicircle gets shifted to the right. At the ground state, all the eigenvalues are positive, and this is a stable critical point.
But won't be there one eigenvalue which will be 0?
Yeah, there is one eigenvalue that is 0. This is a radial direction. This is a simple technical point. This sphere is in an n-dimensional space, but in fact, the surface in which the state of the system lives is n-1 dimensional. See? Because you have the radial direction and then n-1 tangent directions to this hypersphere. So the state of the system lives in an hypersphere, say, immersed in n dimensions, but effectively the sphere is n-1. The dimension of the sphere, of the surface, is n-1. So from the n eigenvalues, one eigenvalues is not important because it is radial. The other, the n-1 that are defined by directions on the sphere, tangent to the sphere, are the relevant directions because the dynamics flows on the surface, on the sphere. This is the spherical constraint.
I see. So the 0 eigenvalue will not be relevant to the...
Yeah, it is not relevant.
Okay,
It is not relevant. Yeah. in more complex models, it happens that there are, in fact, relevant zero eigenvalues that are marginal directions. So kind of channels from which the system can flow, and they are, say, not unstable nor stable. They are marginal. This happens in other models, but not in this model. More questions? Maybe I stop here today, because I would speak about non-reciprocal interactions. That is another topic. And because of the time, I think it is better to leave it for tomorrow. But, well, no more questions or comments? Okay, so let's go to the coffee break and be again tomorrow.